Cool. Hey, folks, welcome back. Just as a reminder, I'm Amanda. I'll be giving the next couple of lectures. And today we're going to be talking about sort of the first class of algorithms for sampling from a model. So we're going to start with this week with sampling and some other sort of classical decoding methods, and then we'll move past there into more modern inference algorithms that require reasoning over multiple decoded tokens at once instead of sort of these token by token decoding. And just as a heads up, I know the website says that homework 1 is coming out today. That will actually be out probably Thursday, and we'll sort of adjust the deadlines to reflect that. So today we're going to be talking kind of exclusively about sampling. We'll talk a little bit about models as probability distributions and some metrics we can use to reason about that, and then we'll use that to talk about sort of two different groups of sampling methods, the first sort of simple and truncation and temperature-based ones, and then a more sort of complex or nuanced method using some of these metrics of probability distributions that we'll talk about first. So as we talked about in the very first class, we can think about a model in a couple of different framings, but the framing that we're sticking with, at least for today, is that a model is just a conditional probability distribution. We're not particularly concerned today with how we arrived at that distribution. We just know, given some input and the prior output tokens, at each step we have a distribution over the vocabulary space for the next token. And under this definition, we can say a couple of different things about this distribution. The first is that the models that we'll be talking about today are locally normalized. What this means is that at each step, we are going to get a distribution over tokens for that individual step, rather than getting something at each individual step that may or may not be a distribution and then having to sort of normalize at the end of decoding. So one way to think about this is that our scores will be monotonically non-increasing. Right, we talked about this in the first class, where if you're multiplying by a number between 0 and 1, your probability will decrease with each additional token. This also means that if you start with a prefix that maybe doesn't look that good, there's no way to add probability mass back in later. So in this example, if you were decoding the US president in 2023 was, and you sort of get the start of this continuation, does the top or the bottom look like a better output so far? The bottom, I see people pointing down, excellent, yeah. So the US president in 2023 was Joseph Biden, looks like a reasonable output. But then maybe if you, like, this sentence sort of wrapped back around, Barack Obama's former VP, we would want to have sort of a higher total probability than Joseph Biden's daughter. Does this mean that in a locally normalized model, the top could never have higher probability than the bottom? No, right? Models learn a distribution over all kinds of sentences. It's entirely possible that this sort of construction is a pretty common way to talk about Joe Biden. And so it's possible that this actually winds up with a higher score, especially because daughter might have a very low weight. But there's no way, once you ascribe a relatively low probability mass here, for this to end up with high probability mass later. It might be higher than this other relatively low probability output, but there's no way to sort of backtrack and say, actually, I think this should have more probability mass. Maybe the beginning was a little misleading. And we can see that as well with this visualization, where the top here is how our models, our locally normalized models work, where these two outputs A and B on each beam are getting assigned probabilities that will sum to 1. In a globally normalized model, you get a score at each step instead, and these scores can be much greater than 1. So here, A gets a score of 3.1. So this like uplifts A over the other candidates in a way that is sort of not possible with a locally normalized model. We do local normalization for a number of reasons. For one, it's very easy and fast to train. You sort of don't have to worry about these constraints on a sequence level. But the sort of flip side of that is that when you want to impose global constraints at inference time, you need to do a little more thinking about how to do that. And in fact, a lot of the methods that we'll talk about for the rest of the semester will be ways of trying to impose global constraints on a model that was only trained sort of with these local normalization. If you're interested in globally normalized models, this figure is from a paper that I've linked at the bottom of the slide, which is a good, if a little bit older, reference on how to do this for sequence models. You can also take PGMs, which has a lot of information about how to do this for graphical models, which is a sort of more common setting. What else can we say about a probability distribution? We also care about some other features of the distribution, and one that we'll touch on a little bit here is calibration. So you may have seen a plot kind of like this before. We say a model is calibrated if the model's confidence score is well correlated with the probability of correctness. So if we have a multiple choice question, the model puts 50% of the probability mass on outputting B. We would like that B to be the correct answer about 50% of the time. And this is useful because then you can take the look at the logits and use that as sort of a direct measure of confidence. Is this a property that our models normally have? Does anyone know? Yeah.
They're pretty reasonable, I think, now, but I think RLHF makes it worse. I think it makes it better. And then it used to be pretty bad, like the earlier models. Like it could be spurious. Like the confidence in the model could be spurious, but the actual performance or correctness.
Yeah, so they used to be worse. They're better now, but RLHF does something to the calibration. Yeah, exactly. So this is actually, this graph is BERT. And you can see this is sort of reasonable calibration. This is GPT-4 on MMLU in particular. And this is a really nice calibration curve. This is the model before RLHF. This is the model after RLHF. Our pre-trained models, if they're relatively strong, if they're trained over a good data set, the likelihood corresponds reasonably well with the truth or the likelihood of that being the true answer. When we do these post-training steps, which are super useful and which generally give us better outputs, they mess with this property of the distribution. So if you're looking at a model that is post-trained, you don't have really a lot of guarantee of calibration. Another feature of probability distributions is that we're generally putting non-zero mass on a pretty wide variety of things. In particular, in these sort of situations where we have a semi-obvious ground truth, we're putting at least some probability mass on incorrect outputs. So your model is not putting 100% probability on 2 + 2 = 4. This can be good, this can be bad. There's some interesting ML theory work on whether this is possible to eliminate entirely. And the answer here is that if you want your model to also have this property of being calibrated, it is not possible to also to eliminate this sort of putting some mass on things that are not factual. And there's a sort of like detailed theory result behind this, which I'll just sort of point you at the paper for here. So those are a couple of properties of our distribution. We'd now like to compute maybe some statistics about the distribution, and these will be useful for the methods that we talk about later. So the first, and one that I think you've probably likely seen before, is the entropy of a distribution, which we're just going to do generally at a single step in decoding, so over the vocabulary space at a single time step, by computing the sum of the probability multiplied by the log probability. If this is relatively high, does anyone know if we have a sort of perfectly uniform model distribution, would we expect entropy to be relatively high or relatively low? All right, we got both answers. High entropy means that we need, this is entropy in sort of the information theory sense, Shannon's entropy. And so high entropy means that we need more bits to encode the information, that there's sort of less of a prior or a bias towards what the most likely outcome would be. So if the distribution is perfectly uniform, we would need a lot of bits to sort of specify any individual thing in the distribution, so entropy would be high. If entropy is really low, it means that there's the distribution is really peaky. So for instance, if the distribution was 100% of the probability mass on one token and 0% on anything else, you could specify sort of your outputs of that distribution very short in like a very brief representation, because you could say it's always token X. And so that would be very low entropy. We care sort of not about entropy just in the abstract. We also care about entropy relative to some ground truth. And here, when we say truth, we usually mean we're looking at some kind of self-supervised objective or semi-supervised objective, excuse me. And so here we calculate something called cross entropy, which is entropy relative to some true distribution. What do we mean by the true distribution? In language models, we're usually looking at next token prediction. And so we look at what the actual next token was in whatever document that we're training on. And we look at the we sort of set a vector where it's 1 if that is the actual next token and 0 otherwise. There's also variants of this where you could sort of smooth that probability mass out. So if you have ever trained a model, you've probably seen the cross entropy loss. And this is exactly this computed over a large set of tokens in a batch. So we multiply a one-hot probability vector with the log probability, which means that this is functionally the negative log likelihood of the correct next token. And if you've ever read a paper about somebody else training a model, you've certainly seen perplexity, which is just 2 to the power of the cross entropy. This is exactly that. There's a sort of interesting connection between perplexity, cross entropy, and the KL divergence between the true distribution and the model distribution, which is something that you guys will see on your first homework. There's a interpretation of perplexity which is presented as intuitive and may or may not be intuitive to you, which is that perplexity represents the odds of correctly predicting the next token if you had a die or a coin that has as many sides as your perplexity number. So if you have your perplexity over some corpus is 6, that means that when the model is predicting the next token, you could roll like a 6-sided die, and every time it rolled a 1, it would get the token right. Every time it rolled another number, it would predict some other token. So that's a couple of different sort of properties of models we'll be working with today. I will pause there for a quick second. Does anyone have any questions so far? Sweet. Feel free to interrupt me if you do. So now we have this distribution. We know a few things about it. We would like to get some output. And the easiest thing to do here, we have a probability distribution. We know how to sample from distributions. And this is called ancestral sampling. And specifically here, we're sampling from the unmodified model distribution. We are just going to draw a sample according to this distribution parameterized by our model. This is great. This is the property that we're recovering the model distribution exactly. And if this is a model we trained, we likely went into quite a bit of effort to get that distribution. So this seems like a kind of reasonable thing to do. And so we're done for the day and we can leave, right? But unfortunately, there's a number of pathologies of sampling directly from the model distribution. The one that we're going to spend probably the most time thinking about today is the long tail. So I originally made a variant of this slide in 2022 or 2023, where it started by saying Llama has 32,000 vocabulary tokens. That's so many. There's so many tokens in this space. There's so many things that have like small probability mass. And since then, this has only gotten to be sort of more of a problem. So now the slide starts that Llama 3 has 128K vocabulary tokens. And this is sort of, and I think a relatively reasonable median for like the vocabulary space of a modern model. If every individual token that is sort of not in the reasonable 100 or 500 tokens to predict next has a tiny amount of probability, these small probabilities add up really, really quickly. And so this is a visualization of that. Where if you can see this little thin line here, that represents the 50% point in the probability mass distribution. So the tail from that point onwards is half of the probability mass. So if you're sampling at every step and maybe you're sampling 100 or 200 times to get a decent little bit of text, the odds of pulling something really, really weird from this really long tail can be pretty nasty. So what do we do to get around that? We saw one option on Thursday, which is to just make the tail sort of flatter or narrower. And so this is the idea of using a temperature to reshape the distribution. So temperature 1 is the original distribution. Temperatures less than 1 sharpen the distribution. So now we have a higher peak and a sort of flatter tail, or less probability mass in the long tail. Temperatures greater than 1 flatten the distribution back out. So if you're looking for sort of more diverse outputs, or if you're looking for more diverse outputs, you can flatten the distribution to increase the odds of pulling something that was otherwise slightly less likely. The other sort of broad class of approaches is if we think the long tail is a problem, we should just cut it off. And so there's a variety of ways of doing this. I know most of you have probably seen a number of these before, so we'll move through them relatively quickly. The first is top K sampling. So we only sample from the K most probable tokens. Depending on how peaky your probability distribution is, this could be quite a few tokens, or this could be quite a bit of the probability mass, or just a little. So here, this sort of running example, we're decoding the first token is the, and we're decoding the next token. There's a variety of things that could go reasonably after the, and so the probability mass in the top 6 is only 0.68. If we then decode car, and then we're looking for the next token after that, the space of things that could reasonably come after the car is a little smaller, and so the top 6 tokens captures 99% of the probability mass. This is a little bit weird that the amount of probability is sort of shifting over time, that sometimes we're capturing just a tiny set of the reasonable options, and sometimes we're capturing even some tokens that have relatively small probability. And so an alternative to this is to define an amount of probability mass you want to capture in your sample instead. So we could say we want 94% of the probability mass. And so for this particular, for the first token here, that's almost all of the tokens in this little graph. For the second token, this is only the first 3. And this is called top P sampling, or this is also sometimes called nucleus sampling. And the intuition is that you start by sort of seeding with the most probable token, and then you add on more and more tokens into your sample until you've hit that much probability mass. And for any one of these, once we've cut off a good chunk of our probability distribution, we no longer have a normalized probability distribution, so you renormalize and then sample from within your subset. Another intuition is that maybe we don't care about having just the highest probability things. Maybe what we're really worried about is only not having the very low probability things. And so this is the concept behind epsilon sampling, which is cutting off the proportion of the tail that has a probability less than or equal to some small epsilon. So here, if everything is at least some reasonable amount of probability mass, you could sample from the full distribution. Here, if there's a number of things that don't have that sort of reasonable amount of probability mass, you would cut those out of the distribution. Of course, this is not exactly a language model here, because we have a distribution over just like 5 tokens, and the tokens we have distributions over change, but just for intuition. And so I figured we could take a look at what this looks like in Hugging Face, which is probably one of the first places that you would go to experiment with a model. And these are all pretty intuitive parameters. You set sampling to true, you set the number of beams to 1, you set top K or top P or epsilon or temperature. There's a little bit of a caveat to this. Does anyone know what the default values of these settings are in Hugging Face?
Top P is 95.
Top P is often 95.
Top K is 50.
Top K is often 50. Yep. This is 50% a trick question, in that, like, I think these are actually the defaults if you don't specify a parameter, but most models will also specify. So I have here llama 3.1 and Quen 3. And if you go into the model files, and you look at the generation config, and you wait a couple minutes to load, models will give you a sort of model provider defined version of these decoding parameters. So llama's temperature is 0.6, top P is 0.9. Quen, I think, sets a top P and a top K. And sets do sample to true. So if you're specifying some generation parameters, it's a good idea to check what the defaults are, check what the model config says they are, and then override everything that you care about. Model providers do this because different models work best with slightly different settings, and they've done some kind of exhaustive hyperparameter sweep at some point to figure out what looks best for their evaluation. So this gives you a sense of what is like commonly used, and also what might work well with that particular model. So that was a couple of more classical decoding algorithms. I want to talk about one example of an algorithm that is a little more complex and maybe a little less widely used, because I think it has a nice intuition on sort of a different way to think about sampling. And to do this, I want to frame a question. So say I have a unfair coin, right? I flip it and it's 60% of the time it lands on heads. I flip my coin 100 times in a row and I sort of write down the sequence of results. Does anyone know what the single most likely sequence of results is from this flipping the coin 100 times? What would be the single most likely result of flipping the coin once? Heads. What would be the single most likely sequence of flipping it twice? Yep, 2 heads. What about the single most likely sequence of flipping it 3 times? 3 heads. So if I flip it 100 times, the single most likely sequence out of all the sequences you could enumerate is 100 heads in a row. Yeah. Would this be a surprising output if you flip this coin? Yes. Why? It's the most probable output.
Also, yes.
Yeah. Right. So this is a little bit counterintuitive. The thing that is most likely to happen is not sort of the expected, or in a very non-rigorous sense, the typical output. What would sort of the typical output look like here? What would you expect to get from this coin?
60 edges and 40 tails and like some point.
Yeah, like some combination that is roughly 60% heads, roughly 40% tails. So this is the notion that the thing that is most likely in our probability distribution is maybe not actually somehow typical of that distribution. To define what typical is requires a little bit more work. So to do this, we're going to draw on a notion of typicality as it's defined in the literature studying stochastic processes. So to do this, instead, we're going to think about our language model as a process that at each step emits a token according to the probability distribution at that step. And then it is now parameterized. Excuse me. It's now conditioned on an additional token, and the process sort of continues. So we're taking some kind of walk through the space of vocabulary by sampling at each step according to our language model. So to define a notion of typicality and to have it be well defined according to this literature, we need a couple of properties from this process. We need the process to be discrete, which means the output space is finite. We need the process to be stationary, which means that the probabilities output by the distribution don't change based on some notion of absolute position. It's okay if they change based on some conditioning from prior tokens, but they shouldn't change based on whether we're like 300 steps into the process versus 0 steps into the process. And we need it to satisfy this property called being ergodic, which means functionally that you can infer the properties of the distribution based on a single long sample instead of a number of small samples that you've aggregated. Functionally, if I took this process and I took a very long random walk, just continuing to sample from it, I would, at the end of that, know sort of all of the properties of this distribution that I care about. For this to be the case, there's one particular thing that has to happen, which is that you must be able to get to any emission or any output from any state. If I want to know the properties of the distribution, I need to be able to sort of look at everything. Once we have these 3 properties, if we assume that we meet these criteria, you can define a couple of things and get to this notion of typicality. So we want to know something called the entropy rate of this process. What this means is rather than looking at the entropy at each individual time step, we'll take a limit as we sort of generate from this process infinitely and average over it. So if your process has the same entropy at every time step, if you're drawing IID samples from the same distribution, this would be the same as the entropy of that distribution. Because we have something like a language model where our conditioning is changing at each time step, this would not actually be that. Yeah. Yeah. So if we, at every time step in this process, we have a distribution and we can calculate the entropy of that distribution. So that's like the notion of entropy we talked about before. But we care about here is not the entropy at any individual step, but sort of the average entropy over time. So if our distribution stayed the same at every step, like that coin that we were flipping, right, that's always 60% heads, then the entropy over time would be exactly the same as the entropy at any step. But because our language model, the entropy of the distribution changes at every step because we've now conditioned on some different text, this is like a measure of entropy over the course of decoding.
You reconcile this with the definition of stationarity which you have? That is, like, probability doesn't change based on absolute position.
Yeah, that's a really good question. Sorry, so the question was, how does this reconcile with like the definition of stationary if the entropy could change over time? And this is a little bit harder to see with a language model because we assume that they're sort of conditioned on everything that's been generated before with a modern model. But you can think about this as, with something like a sliding window or say a bigram language model. Like you care about maybe the X things that came before. And so at step 20, you're conditioned on like maybe the X things that came before. At step 2000, you're conditioned on the X things that came before. But it doesn't matter to the model whether like past the sort of window of things we care about, like maybe past the 20 things if we're a 20-gram model, it doesn't matter how many things happened before that point. So you could think about this as like if you truncated the context for a sliding window or something.
It makes sense under that definition.
Mm-hmm.
But like I'm struggling to see like under the like if you take a modern language model,
Mm-hmm.
how you can have both stationarity and ergodicity. I can't see how both of them can coexist.
How both being stationary and being ergodic can coexist.
Yes, I mean like in a practical sense,
Mm-hmm.
unless you're assuming that it generates infinite, because certain sequences become functionally impossible once you reach a certain length
Mm-hmm.
of the output.
Hold on to the stop for like 20 seconds. This is a really good point. So if we assume we meet these criteria, and we'll come back to them in just a second, we can define something called the typical set for a length and some cutoff epsilon. And the typical set for some length of sequence is all sequences that are exactly that length and that have an average per symbol or per emission negative log probability close to the entropy rate of the process. What that means, if you kind of stare at this a little, is we're going to calculate the log probability. We're going to average it over all symbols, and we want that average to be close to the entropy of the distribution, or to the entropy rate of the process. And here, close just means less than epsilon. So this definition of typicality is, well, maybe like a little weird to wrap your head around, captures this notion that we had from the coin flip that some things that are very probable are maybe not typical. So if you think about the 100 heads in a row, 100 heads in a row is like a very sort of, the log prob of that is actually like fairly high, right? This is fairly probable. But it's sort of not close to the entropy of the distribution, where the entropy of the distribution would suggest that we get something that is a little more like 60%, 40%. This is a really nice definition of typicality. Yeah.
Could you like go back to I mean, I can't see. Sorry.
Oh, sorry. My head is in the way. Yeah, of course. This is a really nice definition. It's got like a really clear formalism. It's got some guarantees as the length of our sequence goes to infinity. Can we apply it to language models? And so to apply to language models, we need to meet a couple of criteria. I think we can agree that a language model you can treat as a stochastic process. We're sampling at every step from a distribution, so that seems pretty reasonable. Is a language model discrete? Right, we have an output space that's finite, which is our vocabulary space, so that seems good. Is a language model stationary? We kind of just talked about this. Maybe it's a little bit complicated if you're assuming you can condition on infinite context. But if you think about a model that has sort of a finite context window, at some point you're going to hit something where there's some past context that is outside of your finite window, and it doesn't matter to your model whether that past context exists or not. It's only caring about the things within sort of its finite space. So we'll say, sure, maybe it's stationary. You know, the probabilities don't really matter based on position. They just matter based on what you've conditioned on. is the language model ergodic? So we said that the requirement for this was that you have to be able to get to any emission from any state. And you seem to think that this is maybe not possible.
I mean, like, it's technically true because everything has a non-zero probability mass attached to it.
Right, so anything has a non-zero probability mass attached to it. So that seems reasonable, right? Maybe you could babble forever. Does anyone see a problem with this, though? It could be like it's a really low probability, but if we've got an infinite amount of time, eventually we'll wrap back around, right? What happens if we generate an end of sequence token? So at least the way that we generally decode from models, if you generate an end of sequence token, you stop, right? And so in the language of a stochastic process, we would say that this is an absorbing state. Probability mass falls into end of sequence and it can't get back out. So if we have an absorbing state, if we have a place that the distribution kind of stops and you can't get anywhere else from there, then you can't get to anywhere from anywhere. You hit the end of sequence token and you need to stop. So this seems like maybe we just went through kind of a lot of math for nothing if we can't use this definition. And so the really nice intuition or method from this paper called locally typical sampling is that maybe if we have this sort of like global typicality as this like North Star that we would like to reach, but if we can't define this in a principled way, maybe we can make like a less principled local approximation and try to get there over time. And so the idea here is that rather than saying that everything over the full sequence needs to be close to the entropy rate, we're just going to say that each new token should be close to some kind of expected amount of information that we thought we'd get out of that token. How do we tell the expected amount of information we wanted to get out of a token? We look at the entropy of the distribution. So at every individual time step, we'll look at the per token entropy, and we'll use that to determine what we sample. The other advantage of looking at this locally is we sample from our models one token at a time. So a global constraint would have been a little bit hard to satisfy anyway. How do we achieve local typicality? We follow this algorithm that looks something like this. So you start by calculating the conditional entropy H, which is the entropy of the logits distribution at whatever time step we're at now. Once you have H, you resort the logits distribution by closeness to H. And when we're working with outputs generated from a language model, we're usually looking at a log probabilities. So this is sort of implicitly resort the log probs by closeness to H. Then we use top P to truncate this new ordering of the distribution. So before top P, we started with our most probable token and we added probability on. Here we're starting with our token that has a log prob closest to H and adding probability on until we hit some value. Yeah.
Like, are we calculating H and checking how close it is to H? Like, I'm not following the symbols we used over here.
Yeah, so H is our entropy. So we're calculating how close the log probabilities are to the entropy and on a per token basis. And the reason that we want to do this is because we're trying to get something implicitly that is close to this, which is the log probability, how close the log probabilities on average are to the entropy rate of the process. So this is sort of like entropy rate is over time. This is log probs over time. We're setting both of those aside and we're just trying to look at an individual time step. And the idea is like if we're close to the entropy of that individual time step, then as we average this over time steps, we should get close to the entropy rate.
So if I understand that correctly, like we calculate the average entropy over the distribution at a particular time step, and then we calculate the individual conditional entropies of each logit, sort them in terms of how close they are to this average entropy, and
close, but I think not quite. So at an individual time step, we can only get one entropy value, and because entropy is a distribution level property. And so we get that entropy by summing over all individual tokens in the vocabulary space, the probability of that token times the log probability of that token. So this is what we're getting from the logits. Once we have that single value, we'll resort the log probabilities by how close they are to that entropy. Yeah, sorry, it's a little confusing because we have this notion of entropy at every individual step, and then we also have the notion of entropy rate, which is like a single value over the whole process. But because we don't satisfy these properties that you need to define typicality, we actually won't worry about entropy rate at all. We'll just worry about individual local entropies. Once we have this new distribution truncated by order closeness to H, we'll sample from that new distribution. And the kind of strange thing about this is that we might wind up actually cutting off, we're no longer sort of cutting off the long tail. We could actually be cutting off things that are relatively high probability. So if you can think about this in terms of if the conditional entropy is high or low. So if we say if we want to make sure the highest probability token is in the locally typical set, is that more likely to happen if we have really high or really low entropy? Does anyone have an intuition for this? So if we have really high entropy, is our distribution peaky or flat? If we have high entropy, then our distribution is flat, yeah. If our distribution is relatively flat, and maybe, just kind of at a slight angle here, would we be more likely to sample from sort of the center of this distribution or from one of the edges, like the peak or the tail? If we're using locally typical sampling, would be more likely to sample from the center or the edges. I hear whisperings of center sort of vaguely hissing in the back, and that is correct. So if our distribution has high entropy and it's relatively uniform, we'd want to sample something that's sort of in the middle of it for a locally typical sampling. If our distribution has low entropy and it's really peaky, then we want to sample something that's kind of close to the edge, because then the log probabilities of the most probable token will be quite low because it's a relatively high probability token. Yeah.
Once again.
Yes. Let me draw this out. So we have two distributions over the next token. This distribution is peaky. Is the entropy high or low?
Low.
Low. And this distribution is flatter. And H is high. Let's say these are the same tokens in the same order, A, B, C. Is the probability of A relatively higher or lower in the top? Probability of A is high. Yeah. Is the is the log probability of A relatively higher or lower than the top right?
Relatively.
Remember our log probabilities, we're taking a log of something that's less than 1, so we're going to be negative. So is it relatively closer or further from 0, I guess? Closer, yeah. So it's closer to 0, which is actually going to be it's going to be more negative, right? There we go. So here it's going to be closer to 0, so the log probability here is going to be higher or lower than
It's going to be higher.
Higher, because it's closer to 0. So if the entropy of this distribution is relatively low, it's going to bias us towards sampling things in locally typical sampling that have relatively low entropy, which means it's going to bias us towards sampling things that are relatively close to the top of the distribution. If the entropy here is relatively high, it's going to bias us towards
it's going to bias us for sampling things that have relatively high log probability, which could be sort of here because we're not at the peak of the distribution, but it's also going to include a bunch of things in kind of the middle of the distribution.
Because the last word, like, why is it moving towards the value of the distribution?
Why is it moving towards the middle?
Yeah.
Yeah, so we're gonna be looking at like you can think of the entropy as defining kind of like a mark on this curve. And so here, if the entropy is quite high, that mark on the curve is going to be relatively high up, and so it's going to be likely to be something close to the peak. Here, if the entropy is relatively low, that mark on the curve is likely going to actually intersect the curve somewhere in like kind of the middle of the distribution. Yeah, thank you for asking, because I think it is helpful to draw this out.
Covered in chalk though. So the reason I keep asking about this is because I think that like entropy, when entropy is high and when entropy is low is really counterintuitive in my brain because it doesn't line up with like when probability is high and low. And so I think it's helpful to like continue reminding yourself of this intuition. So this is the notion of how we achieve local typicality. Maybe we should take a step back and decide if this is actually something we wanted in the first place. And the argument that they make for why this is something that we want to optimize for is sort of like a cognitive science flavored information theory argument. And the argument here is that this is somewhat close to what human language is doing. So to do this, they take a bunch of human language and they calculate these two characteristics. Yeah.
Sorry, like this question. Like if the
Yeah.
probability is higher, how is the log probability further from zero? Then it closer to you, the log graph goes to that. Like they intersect at 1. So if the probability of A is higher, it's closer to 0. Log probability is closer to 0.
Log probability is closer to 0. We've gotten lost in our
Can you go back to the previous slide, please?
Yeah.
What is this question?
If the log probability of A is higher, or if the probability of A is higher, isn't the log prob closer to 0?
No, log probability becomes P of A is higher, then like 1 by P is.
If the probability is 1, let's say, then the log probability is 0.
Yeah, and if it's less likely, then it's more negative.
Yes.
So it's,
So I had this backwards. Well, let's go back. Okay, so let's go back to what we just said. So here, if the entropy is relatively low, the log probability is close to 0. Are we going to get things from the top of the distribution? I think in this case, we will not.
I think only the last line was wrong. I think everything else was right.
Yeah, but can you just explain the last part with this logic now?
Yeah.
Yeah.
Because then this H line is going to be a little bit further down, which means that you are going to sample from possibly not the top of the distribution. Is that true?
If the probability is always 1, you're always going to sample from that one,
Yeah.
because that's typical.
So if the probability is close to 1, you're still, I think, likely to get the top of the distribution, but there is more of a chance of cutting off.
Doesn't this reduce to exactly top P distribution?
Does this reduce to exactly top P?
Yeah, because the log of the function is like a monotonic function. You take the log of it, it doesn't change anything about the relative ordering of the logic distribution. Right? And if you're using top P to truncate it, you're doing the same thing anyways. Like before log, it's the same relative ordering distribution.
Yeah, so the key, the reason this isn't just top P is because of this step 2. Oops, sorry. where you're going to take H wherever it is in the graph, and you're going to like resort your logits by closeness to H instead of by absolute value.
And H will always be less than the maximum log P, right?
H will always be less than the maximum log P.
I guess that then
I believe that's true, but it won't make a difference to the algorithm because you're sorting by closeness to H.
right.
If H was like at top P, then you're right, this would be exactly the same as top P. And I think that's the case Graham is describing where your entropy is 1. Yeah, thank you for touching me on that. So is this actually how human language works? So in this work, they measure the entropy of a bunch of human text and then score it so they measure sort of entropy over time and then entropy at individual time steps, and they graph sort of how well this lines up. Like you can calculate, given a relatively strong language model, the entropy of the logit distribution and then the log probs of every individual token. And they calculate for actual human written text, how often is the human written next token sort of close to the entropy of the logits distribution at that step. And the answer is almost always. So there's some variance here by domain, but generally human written text has the next token relatively close to this like entropy of the token distribution. And the argument that they make here is that this is actually like a way of communicating information effectively, where you don't necessarily always want to say something that is like really unexpected, because then you would just be blabbering nonsense, but you also don't want to say always like maybe the most obvious next thing, because then you wouldn't be conveying any information to your audience at all. Yeah.
It seems very intuitive for like natural language text, but isn't this counterintuitive for factual outputs? Like typically a factual output should would not coincide with the typicality set, like the highest probability token. Is that something that's valid in this theory?
Would a factual output still line up with this theory? Like would if there's a single like really high probability continuation, would this be true? I think this is a really good question. This might be some of the distinction. I think that another part of this is that there is very rarely actually like a single valid next thing. Maybe in something like math or code, this might look different. But in any like sort of natural language description of a fact, there'll be a variety of ways to say it that are more or less typical. Does anyone have a sense of whether sort of like ancestral sampling from a model gives you outputs that are higher or lower perplexity than outputs from something like locally typical sampling? If you think about this sort of like reshaping that we're doing here, do your outputs wind up being higher or lower perplexity with locally typical? You think higher? Yeah, I see a few nods. That's exactly right. Yeah. So what we're doing here is we're reshaping to be closer to the entropy, which is generally not going to be like the very end of this distribution. And so you wind up with outputs that are slightly higher perplexity because of this notion that they're carrying slightly higher information content. And so this is when we're training a model, we want perplexity to be really low because it shows we've learned the distribution well. But sometimes when we're decoding for a model, we want perplexity to be slightly higher. There's a method in sort of the same family of entropy manipulation of models that we won't talk very much about, called mirostat decoding, which is based on the same principle but kind of in the opposite direction, that you should specify a perplexity you want your text to be, and then use a continuously update to try to generate tokens that you think will result in that final perplexity being close to that value. And so these both come from the notion that what we want to optimize is actually some measure of information over time rather than perplexity itself. There's also, to go back to our truncation sampling for a moment, a truncation sampling method that uses this principle. So this is something called eta sampling. And the idea is to impose both epsilon sampling and then some like approximation of locally typical sampling at the same time. So you'll define one threshold based on epsilon, just like as you did in epsilon sampling, and then you'll also define a threshold that moves around with the probability. So this threshold is eta. This is within eta distance from the entropy of the distribution, calculated at that step. And so this is in practice not often terribly different from either locally typical or epsilon sampling, but it's a little bit faster to compute. So this is a whole lot of different ways to sample from the same model. How do you choose? And I really wish that I could just give you an answer here, like always use this and never use this. But of course, we wouldn't be here if things were so easy. So there's a number of different ways to think about this. The first is, I think, pretty intuitive to think about how open-ended the problem is. If you have a problem like write a creative story about a frog, maybe there's a huge range of correct answers to that. And what you care about is maybe diversity of your outputs more than having like the single absolute best story about frog. If you have something that's like explain the solar system to a 5-year-old, maybe this is in the relatively same boat where there's some range of correct answers that is really, really variable. If your question is like, what's the capital of Massachusetts, maybe your options are a little bit more well scoped. I think there's also a lot of value in anything in inference time algorithms and just trying it. These are super, super simple manipulations. They're literally like 8 characters of code to change. And so you can generate a bunch from a small model and try. The caveat here is that smaller and larger models behave very differently. In particular, if you think about model versus search errors, your search errors will be the same for the same decoding method, but your model errors will change radically depending on how well fit your model is to training data that looks like the problem you're trying to solve. So in particular, like smaller models will display a lot of pathologies of sampling that you might not see in a larger model. So try these on the model that you're interested in studying. And then look at the outputs. If you see outputs that look particularly repetitive or degenerate, if you see outputs that start going in a very weird direction, maybe you're sampling from the long tail. If you see outputs that are degenerating into sort of absolute nonsense, you're definitely sampling from the long tail. And if you see outputs that maybe if you sample 100 things and you get the same thing 100 times, or you get very similar things, maybe you want to prioritize diversity, and then you would look at expanding the amount of the tail you're sampling from or something like this. And this is kind of, as I said before, as models have gotten better over time, it's become less crucial where you can sort of take the defaults either specified by that model or specified by a library like Hugging Face and generally get sort of reasonable outputs. If you're working with smaller models or older models, it's like more important to spend some time here. And then the last caveat here is to be very careful what you evaluate your model with, because performance can look very different with different characteristics here. I talked to some friends of mine who work on model evaluation to try to find like a nice uniform answer here. And what they said was essentially what my guess would have been anyway, which is that you should just try a bunch and see. In particular, I've had some friends that are working on training a language model who went and sort of swept through a number of parameters for their eval suite, settled on a sort of range in which their performance of the model was relatively stable across checkpoints, and then set that as the range for all of the evaluations. So it could be like there's often like a region of performance in which these parameters are performance is relatively stable with respect to these parameters. So for them in particular, I think it was like temperature under 7 top P, or temperature under 0.7 top P under like above 0.7 or something. But if you find a range where your model behaves relatively predictably, you pick one strategy, you standardize it across all of your evaluations, because if you overfit to the best decoding strategy for each evaluation, the users who then pick up your model are unlikely to do you the same favor. So this is sort of a caveat for both if you're picking up somebody else's model, but especially if you're evaluating your own, to kind of think a little bit about how you do this setup, because those numbers in those generation configs did not come from chance. So sort of the overarching message here, we can think about decisions on each step of decoding as ways of manipulating or reshaping or resampling from a probability distribution over the vocabulary space. It's really easy to sample directly from this distribution, but reshaping it in various ways kind of avoids undesirable or degenerate outputs. And then do we have any questions before we turn over to student presentations? Yes.
Is it possible that the language model adapts the parameters of the assembly based on the caching?
Is it possible the language model decides the parameters there?
Yeah, decide the parameters and decide the strategy of the assembly based on the caching. So if it's a mathematical question, they can generate something more deterministic. And if it's an open-ended question, they would choose some strategy that might generate more randomness.
Yeah, so is it possible that the language model can like choose a decoding strategy like for itself based on like the type of problem? I have two answers to this, I think, which is I think implicitly language models kind of do this. If you think about like what the probability distribution looks like for over next tokens for 2 + 2 = blank versus like Graham's favorite color is blank, one of those distributions is going to be really, really sharply peaked at a single output, and the other is going to be flatter. And so this is like, in some sense, the model has learned a distribution that is like adjusted differently to the open-endedness of the problem. The other answer is that this is absolutely something you can decide on like a system level. Like if you're receiving prompts from users and then you're passing them to the model, you can change the like generation settings under the hood in between like serving each request. And I think that's like a really reasonable thing to do. I don't know actually of any work or system that does that, but I wouldn't be surprised if like some of the model APIs do. Yeah.
I was curious about the shape of the public distribution of the ancestral public distribution per se. And like, do modern language models, like what are certain, like you were discussing various properties that these models have. I was curious about like, if there are any, if they're extremely sharply curved in certain subregions, but like, are there any specific properties that we can understand, which we can study about this distribution itself?
Yeah, like are there any?
Very, very quickly,
Yeah.
while you answer, for the people who are presenting, could you come up and like start setting up your computer, and we'll continue.
Yeah, I think it's just one today. So
Okay, so the person who is
presenting. Yeah. Yeah, so this is, the question was, are there any properties like that we know of of like the unmodified model distribution? I think the immediate one that stands out is calibration. So we expect the distribution to be peakier if the model is sort of more likely to get that answer correct. Because then that would mean that there's like more probability placed on the single correct answer. It's in terms of like which portions of like the space are more or less likely to be peaky. I would place a personal bet that like if you're doing something related to math or code where there's maybe like a more constrained space of answers, that you would see a distribution that's peakier. But that would just be like a property of how the model learned the data. That's not necessarily guaranteed.
So it's a way to like quantify the jaggedness of like no matter what you prompt this model, there's going to be some amount of jaggedness in the public distribution. There's a way to measure that and probably mitigate that through some sort of decoding strategy.
There's going to be some jaggedness in the distribution. What by no matter what? What do you mean by jaggedness?
It's a discrete distribution. It's a bunch
Yeah.
of histograms. And these histograms are all going to be pretty crooked and jagged. There will be there will also be peaks that you don't expect and some pretty interesting behaviors. I'm just curious about like how you quantify various peaks and if you make out the measure of like how peaky the tail is.
Yeah, like measureless distribution.
Yeah.
I think Entropy is going to give you at least some measure of this, where Entropy will give you some kind of hint as to like how jagged the distribution is. You could also like certainly look at any other statistical property of a distribution. So you could look at things like the mean or median probability mass to a random token. In practice, I think people are usually looking at these distributions sort of like several steps of like granularity further up, where you're looking at something like a measure of perplexity over a corpus, or a measure of like cross entropy over an entire batch. And so you're not necessarily like looking at individual distributions, but particularly if you're doing some kind of task like constrained decoding of like a label in ICL where you care about like the distribution over a single set of outputs, like, or maybe like, you care about the distribution over like A, B, and C, and D for like some multiple choice question, then you can certainly like try to think about properties of that distribution.
Thank you so much.
Of course.
Yeah, one thing I'll mention in addition to this is like jaggedness is not necessarily a problem. So like when you have a reasoning chain, there's like many correct ways to reason about something. And so just because something is jagged doesn't necessarily mean it's bad. And so like because of this, you would think that, oh, like maybe the places with high entropy are like the dangerous places where you might make a mistake, but that's not necessarily the case. Like sometimes the dangerous, like the places with high entropy are the places where you just have many different ways of saying a particular like word or like forming a sentence structure. And then the places where you make a mistake, there's actually just two options. It's like 533 and 534 or something like that. And then that actually doesn't have super high entropy. It's just, log 2. But it's still a problem,
Yeah.
right? So, yeah.
You can actually get kind of a notion of this if you compute perplexity over like a document and you graph it over time. You'll see the perplexity for the very first couple of tokens will be extremely high, to the point where most graphs of perplexity kind of cut off the first 100 tokens or so, or the first 10 or 20, because the options in like starting from nothing are so vast. And then perplexity kind of declines over time and then flattens out. But that certainly doesn't mean that the most mistakes that language models make are in the very first few tokens, right? It just means that there's more valid options in that space. Cool.
Sounds great. And yeah, starting this time, we'll have a presentation. Thank you for being brave and being the person who does it the first time.
Thank you so much.
And everybody, please sign up on this side of sheet. Yes.